Okay, this is a video meant to be a supplemental video for our blog post on the topic of MOSFETs located on the MOTBOT's website titled Understanding MOSFETs, Key Concepts and Practical Examples. I'll leave a link in the description below to that reading material if you're interested in this particular topic. I've actually already created this video once and posted it, but thanks to a very informative comment made by Rex Schneider, I was informed of a mistake I'd made on the original circuit that I created for this blog post. I ended up having to correct that mistake, which changed some of the component values for this particular circuit here, as well as the calculations, which is why I'm creating this second video here. But all should be in order now, and all has been promptly corrected on the site. At least I hope that it is. I tend to make quite a lot of mistakes, especially with stuff like this, so we can only cross our fingers here. So it's always a learning experience, which I always appreciate that. By the way, that mistake video is still up. I didn't take it down, so if you're interested in seeing it, I don't know why you would be interested in seeing it. I mean, there's still some valuable information in there, I guess, but it's pretty much the same video that this one's going to be, but with the obvious corrections here. So you can choose to do so if you'd like to. I'll leave the link to that video here too, down in the description below. Anyway, what we have here in front of us now is a breadboard with our MOSFET circuit. And it's already all connected up here. This is the exact same circuit setup that you can see here. And that circuit, like I said, is the exact same circuit on the example switch application for this particular MOSFET that we did on that post. Again, I'll leave the link down in the description below, which is where you can also find the schematic for this setup as well. So if I zoom you in here a little bit, and I'll reposition this, maybe if I move this sheet of paper out of the way real quick, we'll be needing that later, just not right now. Let me zoom in a little bit. Now that we're zoomed in, I can kind of briefly go over the setup here. So I tried to set this up on the breadboard almost exactly like it was in the schematic that is on the website, that's provided on the website. I know you can't see that in the camera right now, but here I have my battery source. It's a 9-volt battery, and the two terminals coming off that battery, the red terminal is the positive supply, and the black lead or terminal is the negative supply. And if we follow that red wire, the positive supply, it goes to the positive supply rail or power rail of the breadboard here. And then I've also continued that supply using this orange jumper wire here and continued it over to the other positive power rail on this breadboard. And again, going back to that positive lead of the battery, it goes to the positive power rail to this yellow jumper wire that goes to a lead on this push button switch, a normally open push button switch on this end, and then the other terminal on the other side of that push button switch is in line with this yellow jumper wire, which is in line to the lead of this resistor here. This is resistor R1 in the schematic. Again, you can find that schematic on the website. I'll leave the link to that down in the description below. This is the 1K ohm resistor, resistor R1, and the other lead of that resistor is in line with the gate of this 2N 7000 MOSFET, and the gate lead is the center lead. I know you can't see it from the view that you're at, but the lead to this 1K ohm resistor goes to the center lead of this MOSFET, and that is the gate. Also in line with the gate is the lead of this resistor here, and this resistor represents resistor R2 from that example circuit in the schematic. This is the 2K ohm resistor that we find the value for in that example switch application. And then the other lead of this 2K ohm resistor goes to the negative supply or negative rail of the breadboard here. And I forgot to mention that the negative rail on this end of the breadboard is also connected with this black jumper wire, and it goes to the other negative power rail on this side of the breadboard. So looking back at the MOSFET again, if we look at its drain pin, which is from your view above the circuit here, it's this right side pin, and it's in line with this resistor here. These two resistors are in series, and they're representing my 200 ohm resistor, which is resistor R3 in the schematic. These are two 100 ohm resistors that when set in series add up to 200 ohm or 200 ohms. So that drain lead of the MOSFET is in line with this lead of this 100 ohm resistor, which is in line with this 100 ohm resistor, making up 200 ohms together. And the end of this resistor is in a point on the negative supply rail of the breadboard. Looking back at the MOSFET on its source pin, which is this left pin from your view above here. I know you can't see the pins, but it's on the left side as the MOSFET is currently oriented. And that source pin is in line with the anode, or excuse me, the cathode of the LED. And then the anode lead of the LED goes to the positive power rail on this side of the breadboard. And here in a little bit, I'll give you a more close-up view so you can see how everything's hooked up and the placement of everything as it is right now. I know that it's a little difficult to see how things line up from a top view, but again, I'll give you a different view later on in this video. So again, this was for the switch application example in the blog post. And if I were to press the button here, we could see that the green LED lights up. And this is all controlled thanks to this N-channel enhancement mode MOSFET. And again, an enhancement mode means that it's normally off. So as you can see here, if I'm not pressing the button, the LED is currently off and nothing's happening. If I press the button, the LED comes on. And all that is explained in that blog post that I mentioned. And again, I'll leave all that in the description below. But you can follow along in that reading material and set up your own circuit just like this one for the switch application using the 2N7000 MOSFET. In that example, we're given some values of the circuit and we're asked to find some unknown values. In this case, we're asked to find the resistor value of R2, which is this resistor right here. This is the 2K ohm resistor, and that's the value that we found in that example problem. And we're also asked to find the drain to source voltage. If you haven't read that blog post, all this may not make a lot of sense right now, so I encourage you to go check out that link and follow along with this example circuit here. Everything would be much more clearer if you did. I just wanted to show you this completed circuit, the working circuit here, real quick, and kind of go over the circuit and share it with you. But before I let you go, I just wanted to go over something. So I'm gonna move this out of the way and I'm gonna zoom you back out. And I wanna bring back this schematic here. Maybe I'll zoom you in just a little bit more. So in the example schematic or the example problem on the blog post, we're given values like the 9-volt power supply. We're given that we're going to be using a drain current value of 20 milliamps. We're given that the voltage drop across the LED in the circuit is 3 volts, and we're given values like the resistor value for R3 of 200 ohms, the resistor value of R1, which is 1 k ohm, and like I said, we're asked to find the value of R2 and the value of the drain to source voltage. Now these values are already in place here. This is just to help me out in discussing this example problem. But based on the values given, what we were able to do is to figure out the voltage drop across resistor R3, since we know the value of the 200 ohm resistor and we know the value of the drain current of 20 milliamps. Looking at the circuit, we would know that the drain current going into the drain of the MOSFET, it would be the same value of the current coming out of the source of the MOSFET. Hence, the source value is equal to the drain value, which is equal to the 20 milliamps. So in knowing that the source current is 20 milliamps and the value of resistor R3 is 200 ohms, then we can use Ohm's law to find the value of the voltage drop across R3. So if we were to multiply the 20 milliamps times the 200 ohms, we would get a value of 4 volts, or that would be the voltage drop across resistor R3. And in that example problem on the blog post, we were given that the gate source voltage is 2 volts. So in knowing that the gate source voltage is 2 volts, and then us figuring out that the voltage drop across R3 is 4 volts, the sum of these two voltages is 6 volts, because we could take the sum of the two voltages because they're in series here. So that means that the voltage potential across these 2 points between the gate and the negative supply or ground of the circuit, you can see that all of the negatives go to this node of the circuit, that we can say that these 2 points between the gate and the negative supply, and these 2 points across resistor R2, the voltage drops or the voltage potentials should be equal. So that's why, or how, we got the value of 6 volts across R2, because 2 volts plus 4 volts is 6 volts. That's the voltage potential between these 2 points, which should be the same voltage potential across these 2 points because they're in parallel, and voltage potentials in parallel with each other are equal to each other. So 6 volts across these 2 points, 6 volts across these 2 points. So now in knowing that the voltage drop across R2 is 6 volts, we can't quite figure out what the value of R2 is because we don't know the value of R2. That's what we're trying to figure out. And also, we don't know what the value of I is through R2. But since we do know the voltage across R2, and we know the voltage value of the source for V1, then the voltage drops across R1 and across R2, since this circuit here is considered a series circuit, this loop here, the sum of these two voltage drops should equal to the source voltage of V1. Now, even though it's the voltage drop across R1 is given here in this print off, we didn't originally know what this value was. So in order to find out what the voltage drop was across R1, the sum of whatever this voltage drop is plus this voltage drop should equal to 9 volts. So if I have 6 volts here, this must be 3 volts across R1, because 6 volts plus 3 volts is 9 volts, which is equal to the voltage value of the source voltage of V1. So now that we knew what the voltage drop across R1 is, then we can figure out what the value of the current is coming from our source voltage going through resistor R1. Again, we'd use Ohm's law for that. Since we're given the value of R1 to be 1K ohm, we'd divide the 3 volts across R1 by 1K ohm, and that would give us a current value I of 3 milliamps. And like I said, this loop of the circuit is in series because that current value is not going through the gate, because a gate of a MOSFET acts as a capacitor. So there's we can just say ideally that there's no current going through the gate. Therefore, the current is going through this section of the circuit here, and this is a series circuit. So if this is a series circuit, whatever current is going through resistor R1 is also the same current going through resistor R2, and that is just the current I, which we just found to be 3 milliamps. So now that we know the value of I, and we know the value of the voltage drop across R2, we can again use Ohm's law to find what the value of R2 is, and that's just the 6 volts divided by the 3 milliamps, which gives us a resistor value of 2,000 ohms or 2 kilo ohms. Although I didn't put that value in here, but that's the value of the resistor R2 that we were able to figure out in that example problem. And then again, we were asked to find what the drain to source voltage was across the MOSFET. So all we would need to do there is again use Kirchhoff's voltage law. Since we know what the value of the source voltage is here, it's 9 volts. We were given that the voltage drop across the diode or the LED was 3 volts. And we found that the voltage drop across resistor R3 was 4 volts. This portion of the circuit is a series circuit, so the voltage drops across these components of the circuit should equal to the source voltage of V2. So 3 plus 4 is 7. So that means that the value or the voltage drop across the drain and source of the MOSFET should be 2 volts, because 4 plus 3 is 7 plus 2 is 9 volts, which is equal to the 9 volts, the source voltage for V2. So I just wanted to kind of go through that real quick. This being from the exact same problem from the blog post. This is based on ideal conditions, and I thought it'd be neat to go over the real world conditions of our real world circuit that we have here. So what I did is I took my multimeter and I took the probes, and what I first did before hooking the battery up to the breadboard is I took my probes and I measured the voltage across the battery terminals, and that gave me the source voltage of 8.15 volts. I'm obviously using one battery here, although it shows 2 batteries in the circuit. I'm using one for my circuit here on the breadboard. So in that case, V1 and V2 is 8.15 volts, which is the reading I got from my multimeter reading. And then what I proceeded to do is, before I put the resistors into the breadboard, is I took my probes and placed my multimeter into its resistance reading mode, and I took resistor reading values across each one of the resistors out of the circuit. And for my 1K ohm resistor, resistor R1, I ended up getting a reading of 979 ohms. I took a reading, and that was this resistor here, the 1K ohm resistor. I took a reading of resistor R2 and got a reading of 1,955 ohms, even though it's labeled as a 2K ohm resistor. And then again, I'm using 2 100 ohm resistors to make up for the 200 ohm resistor value of R3. And I took measurements across each one of these resistors, one being 88.3 ohms, another reading for the other resistor being 87.9 ohms, and the sum of those two values gave me a value of 176.2 ohms and not 200 ohms. So those are the real world values of resistor R1, R2, and R3. And then with everything hooked up in my circuit and the button pressed, I took voltage readings across the LED, and for the LED I'm using, I got a voltage drop of 2.05 volts. I took a voltage reading across the drain and source of the MOSFET, and the voltage reading I got from the multimeter was 2.51 volts. And then I took a voltage reading across resistor R3, which is across these two 100 ohm resistors here, and I got a voltage reading of 3.45 volts. So again, Kirchhoff's voltage law says that the sum of the voltage drops, in this case across the diode, across the LED, and across the drain and source of the MOSFET, and across resistor R3, those voltage drops, the sum of them should equal to my source voltage, which is 8.15 volts. And if I were to add 2.05 volts plus 2.51 volts plus 3.45 volts, I get a value of 8.01 or 8.01 volts, which is pretty darn close to the 8.15 volts. So we may be able to determine that there's maybe some voltage losses going on here in the circuit. We might have to consider the internal resistance of the battery and things like that, but it's pretty much 8 volts equals 8 volts in this case, which turns out pretty good for this real world scenario. And going back to taking voltage readings, I ended up taking my probe and making some voltage readings across resistor R2, and I got a voltage of 5.4 volts, and then I took my probes and I took a voltage reading across resistor R1, and I got a voltage reading of 2.69 volts. And again, using Kirchhoff's voltage law, the sum of the voltage drops across these two resistors should equal to the source voltage of 8.15 volts. And if I were to add 2.69 volts plus 5.4 volts, I end up getting a voltage value of 8.09 volts, which is, again, pretty darn close to this 8.15 volts. And again, we might be needing to consider some voltage losses within this part of the circuit here. Again, the internal resistance of the battery source, so there's that. But as for, I just wanted to show this for the real world values and their readings using a multimeter. I just thought it'd be neat to kind of show that at least, and not just go over your typical theoretical ideal circuit that was given in the blog post. But what I'd like to do in future material or content is put something out on the website and probably make a video later on that will be a companion to that content on maybe some questions and answers on circuits like this for MOSFETs, questions that I had when I first started tinkering around with MOSFETs. You know, maybe some questions like, why do some MOSFET circuit diagrams show 2 voltage sources and not 1 like the one I'm using here? Do I need to use 2 batteries in this case? Do I need to use 2 9-volt batteries? Can I use 1 9-volt battery? I'm obviously using one here for this one, but when you're starting out, this may be questions that you're asking yourself when you're first learning stuff. It's certainly questions that I had. Like I said, is it okay to use 1 9-volt battery for this particular circuit, or do I have to use two 9-volt batteries? Is it okay? Am I going to get different voltage readings? Would using a single 9-volt battery affect voltage readings throughout the circuit? instead of using 2 batteries? Or would those voltage readings across components read the same either way? So I think it'd be beneficial for some folks, maybe, maybe not. I certainly think it would have been beneficial to me, for myself, and my own learning experience when I first started out. So I'm thinking of doing something like that later. I'm just kind of brainstorming right now, but the main focus is for this particular circuit, and I just wanted to kind of go through the real world stuff, not only the stuff that was given on the blog post, but I hope this was beneficial to you. So I hope you go check out that blog post, Understanding MOSFETs, Key Concepts and Practical Examples. And I'll leave all that information that you need to know for that down in the description below. And what I'll do now is I'll leave you with another view of pressing the button and watching the LED come on. And like I promised, I'll get you a close-up of this too. Okay, we're at a more close-up view here of the circuit, and I tried to tilt it as best as I could so you can kind of get a decent view of the connections there. But before I leave you, I'll sit here and press the button here again so we can see the LED come on and watch the circuit working. Isn't that neat?